Okay guys, today's lesson is going to be on functions. Let's just talk about a couple of terms. The first one here is a relation, and a relation is just a set of xy pairs that don't necessarily have really any correspondence to each other. Then we have a special kind of function, a special kind of relation, which is called a function, where each x corresponds to exactly one element in the y. So basically what that means is no repeating x's. The domain is our set of x values. The ranges are a set of y's. D comes before R in the alphabet. X comes before Y in the alphabet. That's one way to remember it. X is also a set of inputs and outputs. And that also flows with the alphabet. I comes before O. X comes before Y, D comes before R, so that's how just one way to remember those guys. Let's look at a couple of relations and determine whether they are functions or not. So I'm looking at this function here. The first thing I notice is that 2 is paired with 5, 2 is paired with 7. We see we have those repeating x values, so the answer to this is no, it is not a function. 2 maps to more than one y value. Alright, let's take a look at B. I'm scanning through the x's here. I see no repeating x's, which means each x value is paired with exactly one y value. So the answer here is yes, this is a function. Each x maps to exactly one y value. Looking at this guy over here, I guess we really should call that C, but anyway, A maps to 2, B maps to 1, C maps to 2, D maps to 3. There are no repeating x values. It is okay for two separate x's to pair to the same y. That is still a function. So again, here the answer is yes, and the same would be the reason each x maps to exactly one y. If you look at your x values here, negative 1, 2, 3, these guys are also no repeating x's. Another thing we call the vertical line test. And if I were to move a vertical line, if you think about a pencil passing through, it only passes through one point. So here the answer is yes. You could say pass vertical line test, or you can write what's right up here. Either way would work. Function notation, that is read f of x. It does not mean times x. X is going to be our independent variable. Y is a dependent variable, and it's dependent because it depends on which x we input inside there. A relation is not a function if we have any repeating x values. Okay, so let's take a look at this. The first thing I want to know is what is f of 2. So any place I see an x, I'm going to replace it with 2. So it's going to get me 3 times 2 squared plus 1. It's going to be 3 times 4 plus 1. So I get 13. So f of 2 is 13. When the x value is 2, the y value is 13. For B, they're asking us to add these guys together. So f of x is just what this is over here. So that is 3x squared plus 1 plus f of 2. We already found that in the problem before in A, so we found that to be 13. So I get 3x squared plus 14. For C, I'm going to replace this x with x plus 2. So it's going to be 3 times x plus 2 squared plus 1. Remember to FOIL out when you're squaring the binomial here. So 3 times x squared plus 4x plus 4, plus 1. Distributing the 3x squared plus 12x plus 12 plus 1. And then combining up the like terms here. 3x squared plus 12x plus 13. Let's look at these last few here. I want to know what is f of negative x. So again, wherever I see an x, we're going to replace it with negative x. So we're going to have 3 times minus x squared plus 1. And when you square a negative, it becomes positive, so we wind up with the exact same function. Here we're looking for negative f of x, which means we want to take the entire function and negate it. So that means that negative will need to be distributed to both parts. Minus 3x squared minus 1 is what we get here. This here is something that you're going to be using in calculus quite a bit. Right now we're just learning the mechanics behind it of how to find that. So what we're looking at is first replacing the x with x plus h. So we're going to have 3 times x plus h squared plus 1 minus. Whenever I'm minusing up more than one term, I like to put up a big bracket so that I remember to distribute to both parts, and all that's going to be over h. F of x is just the function up there. Now let's go ahead and multiply this guy out. So it's going to be 3 times x squared plus 2xh plus h squared plus 1 minus, and I'm going to go ahead and distribute now, 3x squared minus 1. Here the 1's cancel out. All this is still over h. Let's distribute the 3 plus 6xh plus 3h squared minus 3x squared, still all over h. Now the 3x squareds are going to cancel. Continuing on, what we're left with at this point is 6xh plus 3h squared all over h. And I have an x in all three terms. In order to cancel it, must be present in all the terms. We're going to be left with 6x plus 3h. Okay. Moving on to the next side, we are looking at just two different, really, vocabulary here. We have an explicit form where the y is isolated. We have an implicit form where you have both x's and y's in there. So I'm looking at this equation here, and I want to know, is it a function? It would mean I would have to get it to the explicit form and solve for y. So that would mean y squared is equal to negative 2x plus 3. Taking the square root, y would equal plus minus negative 2x plus 3. And the fact that I have a plus minus here means that there are two x's mapping to the same y. So the answer would be no for that very reason. I have two x values mapping to the same y. If you think back to our conics unit, though, if we had a y squared parabola and it was negative, it would be opening this way. And therefore, it would fail the vertical line test. We also need to kind of remind ourselves about domains. Finding the domain of each function here. What we're really interested in are denominators, because denominators cannot be 0, or radicals, because we cannot take the square root of a negative number. I'm going to write both of these in set notation and interval notation. We'll be using more of the interval notation throughout the course. When I look at A here, I don't see any denominators and I don't see any radicals. Therefore, there's no domain restrictions. So the domain is going to be negative infinity to positive infinity, or in set filter, x, where x is greater than negative infinity and less than positive infinity. For B, however, though, x cannot be negative 1. The reason it cannot be negative 1, it would drive this denominator to 0, and that's just not okay. So our domain is going to be from negative infinity, traveling all the way through to negative 1, picking up on the other side of negative 1, and going to infinity. These soft brackets here mean that we don't include negative 1, we just get as close as we possibly can. In set builder, it would be x, where x is not equal to negative 1. Our last problem here, C, it's a radical. So the radicand, the stuff underneath the radical sign, cannot be less than 0. So 3 minus 2t has to be greater than or equal to 0. We do want to put that or equal to because we can take the square root of 0. Solving here, we get negative 2t is greater than or equal to negative 3, and t is less than or equal to 3/2, flipping that inequality sign when dividing by a negative. So long as t is less than or equal to 3/2, this will remain positive in here. So an interval going from negative infinity to 3/2 into hard brackets, we are allowed to include the 3/2. Or, as far as set notation goes, it's going to be x where x is less than or equal to 3/2. The last thing we're going to do is just some couple operations on these functions. We can add them, we can subtract them, we can multiply them and divide them. Our two functions that were given here are f of x and g of x. Here I'm asked to add the two together. So I have 2 over x plus 1. I'm going to add that to x over x minus 1. In order to add or subtract fractions, we need common denominators, and the common denominator is going to be x plus 1, x minus 1. We do want to leave the denominator in factored form. It's easier to see what it can't be. Now if I look here, this has the x plus 1, but it's missing the x minus 1. So I need to multiply both top and bottom by x minus 1 to achieve this. So it's going to be 2 times x minus 1. On this side, I have the x minus 1. What we're missing is the x plus 1. Distributing in the numerator. Still over x plus 1, x minus 1. And then just combining up our like terms, we get x squared plus 3x minus 2 over x plus 1, x minus 1. The numerator is unfactorable, so we are done there. It is asking for the domain of each. So whenever we have combined things like this, we want to first look at the original functions. For f of x, x cannot be negative 1. And for g of x, x cannot be 1. So for all four of these sitting here, that's going to hold true. Then you want to look at the combined function and see if anything else is added in. And it's not. We still just have those two functions in the denominator here. So our domain is going to be from negative infinity to negative 1, picking up on the other side of negative 1 going to 1, and then 1 to positive infinity. Okay, so looking at b, we kind of want to do the same thing, but the only thing that's changing is the fact that we're subtracting. So now it's going to be 2 over x plus 1 minus x over x minus 1. Still needing the common denominators of x plus 1, x minus 1. Again, this one's missing the x minus 1. Again, like I said before, and once you're subtracting, put up that big bracket to remind yourself that it has to be distributed. This is going to be x, and we're missing the x plus 1. Distributing here, 2x minus 2. Still leaving up that bracket, x squared plus x. Denominator does not change. Let's do the final distribution. Get minus x squared minus x, still all over x plus 1, x minus 1. And the last thing we need to do is combine up like terms. We have minus x squared plus x minus 2, all over x plus 1, x minus 1. Remember, it's denominators and radicals that concern us here. So I'm only looking at this denominator. Nothing new has been added in but the minus 1 plus 1. So this guy would have the same domain as this guy over here. In the next problem, we're asked to multiply. So I'm going to take f of x. I'm going to multiply that to g of x. I guess I really don't need the parentheses there. X minus 1. When we multiply fractions, we multiply the numerators and we multiply the denominators. Again, leaving this in factored form here. There's nothing else that will simplify. Again, looking at domain, I've not added anything new to this domain here, so it's still x cannot be 1 and x cannot be negative 1. And again, giving us that same domain of negative infinity to negative 1, union with negative 1 to 1, picking up again with 1 to infinity. Okay, this last problem here, we are asked to divide. So I'm looking at 2 over x plus 1 all over x minus 1. And when I have these fractions inside fractions, I'd like that middle fraction bar to be nice and big to distinguish and kind of make it clear what's in the top, what's in the bottom. I don't like to deal with these very much, so what I like to do is wipe out these denominators. So I'm going to multiply everything through by the greatest common multiple, which is x plus 1, x minus 1. And if I multiply the top, I also have to multiply the bottom, because this is now a 1 equivalent. So anything times 1 is the same value. I'm not changing the value of this combinations division here, just the way it looks. Here the x plus 1's cancel. We get 2 over x minus 1. Here the x minus 1's cancel. And this is what we're left with here. So let's go ahead and distribute on the numerator, but not in the denominator, because we want to see what things can't be. Now, from the original functions, x cannot be negative 1, and x cannot be 1. That still holds. We would have never been able to divide them in the first place if those two domains existed. We have added, though, this plain x here. So now x can also not equal 0. So written in interval notation, this is going to be a big one. Going from negative infinity to negative 1, picking up on the other side of negative 1 to 0, the other side is 0 to 1, and then 1 to infinity. And with that, we are concluded with this lesson.